Welcome back to Math Kernel. Last time we built the scalar product and the norm. Today we cache them in and watch a whole world of geometry fall out of just 3 axioms. One inequality, real angles, and a couple of theorems that are 2,000 years old. Everything today flows from a single algebraic move. Take 2 vectors, add them, and ask for the length of the sum, squared.
So we're standing at the far corner of the parallelogram, the tip of x plus y, and asking how far that is from the origin.
Exactly. Write that squared length as the vector's product with itself, and expand it, exactly like multiplying out a bracket. Bilinearity splits it into 4 pieces. Symmetry merges the 2 middle ones, and out comes norm of x squared, plus twice their product, plus norm of y squared. It's the binomial formula for vectors.
Wait, I want to make sure we didn't cheat. We never wrote down a single coordinate there. Where did that expansion actually come from?
Only the axioms, bilinearity to split, symmetry to merge. No coordinates anywhere. And that's the point. Flip the plus to a minus, and just one thing changes. The middle term flips sign. These 2 expansions are the engine behind every identity today.
2 formulas that differ by 1 sign. That feels like it's asking to be added and subtracted.
You're reading my mind, but here's an immediate gift first. Multiply the sum by the difference. The cross terms cancel by symmetry, leaving just norm of x squared minus norm of y squared. The difference of 2 squares in vector form. So the takeaway is small but total, 1 bracket expansion, driven purely by bilinearity and symmetry, and everything that follows is just this move, reused. Now the crown jewel of the whole subject, the Cauchy-Schwarz inequality. Its proof is a magic trick with a parabola, and it leans on nothing but positivity.
A parabola? We're comparing a product of 2 vectors to a product of 2 lengths. Where does a curve even come from?
We invent one. Fix x and y, and slide a single number t. Look at the vector x minus t times y, and take its squared length. That length can never be negative. That's the positivity axiom. So this function, g of t, sits on or above the horizontal axis for every single value of t.
Fine, it's non-negative. But a curve staying above a line, how is that an inequality about the product of x and y?
Watch it turn into 1. Expand that squared length with our binomial rule, and g of t is a quadratic in t, an upward opening parabola, because the leading coefficient is norm of y squared, which is positive.
Upward opening, so it has exactly 1 lowest point, and it never comes back down.
And 1 line of calculus finds that lowest point. T star equals the product of x and y, divided by norm of y squared.
Here's where I'd try to break it, so what if the minimum is low? Why does the argument die there?
Because the whole curve stays at or above 0, so its minimum value is at least 0 too. Substitute t star back in, clear the denominator, and that single fact rearranges into the product of x and y squared is at most norm of x squared times norm of y squared. Take the square root, and there it is. The size of the product is at most the product of the lengths. Cauchy-Schwarz.
An equality? When does the inequality become an equation?
Exactly when the parabola dips down to kiss the axis, when x minus t star y is the 0 vector. That means x and y are parallel. The curve touching 0 is the algebra for pointing the same way. A 30-second check to trust it. For 2, 1, and 1, 1, the product is 3, and the lengths are root 5 and root 2, whose product is root 10, about 3.16. 3 is under it. The inequality holds, with a sliver to spare. Cauchy-Schwarz pays a dividend right away, the triangle inequality. Going straight from here to there is never longer than detouring through a third point.
That's the picture on the board. The green arrow goes direct. The blue then violet path takes the corner. The claim is the corner route is never shorter.
And here's the strategy. Both sides are lengths, so both are non-negative, which means squaring the inequality can't flip it. So we prove the squared version instead, where our expansion lives.
So expand the left-hand square, and I'll want to know how the cross term gets controlled.
Expand it. Norm of x squared, plus twice the product, plus norm of y squared. Everything hinges on that middle term, twice the product of x and y. Now two small bridges, and you need both. First, the product of x and y is at most its own absolute value, because it might be negative. Then that absolute value is at most the product of the lengths, by Cauchy-Schwarz.
2 steps, not 1, because skipping straight to Cauchy-Schwarz would ignore that the product could be negative in the first place.
Precisely why we spell both out. Substitute, and the right side folds up into exactly norm of x plus norm of y, all squared. Take the root, and the shortcut wins. 4, 3, 4, and 1, 0. The direct length is about 5.7, comfortably under 6. So, to bound a length, square it, expand, and let Cauchy-Schwarz tame the one cross term. That recipe is the triangle inequality. Those same two expansions hide something deeper. Draw the parallelogram spanned by x and y, and look at its two diagonals, the sum, in green, and the difference, in orange.
So the two diagonals of one parallelogram are exactly x plus y and x minus y. That's a satisfying picture.
Now subtract their squared lengths. The norm squared terms cancel, but the two middle terms don't, they double up. You're left with 4 times the product of x and y.
So you can recover the product from lengths alone. Does that mean the product carries no information the norm doesn't already have?
That's exactly the punchline, the polarization identity. Rearrange, and the scalar product is 1/4 of the difference of the two diagonal lengths squared. Product and norm are two views of a single structure. Now add the squared diagonals instead, and the opposite happens. The middle terms cancel, leaving twice norm of x squared plus twice norm of y squared. The parallelogram law, the two diagonals know the 4 sides.
So is that just a pretty identity, or does it actually decide something?
It decides everything. Jordan and von Neumann prove that a length function comes from a scalar product if, and only if, it obeys this law. It's a lie detector for norms.
Then give me a norm that fails it.
The taxicab norm, add the absolute coordinates. It breaks the parallelogram law, so it hides no scalar product and no angles, a space with distance but no protractor. An abstract vector space doesn't ship with a protractor, so we build one. We define the angle between two vectors using nothing but the scalar product.
And the definition is the old high school formula. Read backwards. Cosine of the angle is the product over the two lengths. But is that allowed? You're defining cosine of something. Cosine only lives between -1 and +1. What stops that fraction from being 2?
Nothing stops it, except Cauchy-Schwarz, which is the whole reason we proved it. The size of the product is at most the product of the lengths, so that fraction is trapped between -1 and +1. It's a legal cosine. Without that inequality, the definition would be nonsense. And because cosine is 1-to-1 from 0 to pi, the angle it names is pinned down uniquely.
So read off the corners. Cosine 1 is angle 0, same direction. Cosine -1 is 180 degrees, dead opposite. And the middle, cosine 0?
The most important case of all. Cosine 0 means the product is 0, and that is orthogonality, a right angle, defined by algebra alone, with no picture required. Make it concrete. 4, 1, 2, and 3, 1. The product is 5. The lengths are root 5 and root 10, and the cosine comes out to 1/√2. The angle between them is 45 degrees. So the scalar product doesn't just measure length, it hands you every angle, and it hands you the right angle as simply the case where the product vanishes. The angle definition hands us the law of cosines almost for free, and not just in the flat plane, but in any space carrying a scalar product.
The triangle on the board, two sides are x and y from the origin, and the third side, in green, joins their tips, that's x minus y, sitting opposite the angle.
So take that third side's squared length as its product with itself, and expand with the binomial rule, norm of x squared, minus twice the product, plus norm of y squared.
That's just the difference expansion again. What turns it into the cosine rule?
One substitution. Swap that product for its angle form, length times cosine phi. And there it is, the opposite side, built from the other two sides and the angle between them. The law of cosines, straight out of the axioms.
And if the angle is a right angle, the cosine dies and something famous should appear.
It does. Set phi to 90 degrees, the last term vanishes, and what remains is Pythagoras. The oldest theorem in geometry is just the cosine rule with a right angle, and now it holds for functions, for matrices, for anything with a scalar product. So one identity contains two, the law of cosines in general, and Pythagoras the instant the product is zero. Angle in, geometry out. Let's finish with a 2,000-year-old theorem, proved in 3 lines. Thales, put the two ends of a diameter at A and B, and pick any point C on the circle. The claim is that the angle at C is always a right angle.
Always, any C on the circle, and the corner at C is a perfect 90 degrees. That's a strong promise.
And a right angle at C means the two legs, C minus A and C minus B, have scalar product 0. So we just compute that product and see what it takes. Expand it with bilinearity. The cross terms gather into the product of A plus B with C, and we're left with norm of C squared, minus that, plus the product of A and B.
That's a mess of 3 terms. What collapses it?
One clever observation, and it's geometric. A and B are opposite ends of a diameter through the center, so A plus B is the 0 vector. That whole middle term simply vanishes. And the product of A and B works out to minus R squared.
So we're down to just 2 survivors.
Norm of C squared, minus R squared. And that's 0 exactly when the length of C equals R, when C lies on the circle. So every point on the circle sees the diameter at a right angle.
Every point or just the tidy one you drew? Show me it isn't special.
Watch, I'll slide C right along the arc, completely different position, and the legs stay locked at 90 degrees, because the same 3 lines never used where C was, only that its length is R. That's Thales. So a right angle on a circle is nothing mystical. It's just the diameter forcing the product of the 2 legs to vanish wherever C sits. Let's gather it up. One inequality sat at the center of everything today, Cauchy Schwarz, with equality exactly when the 2 vectors are parallel.
And from it we drew real geometry out of 3 bare axioms, the triangle inequality, and an angle whose cosine is forced to live between -1 and +1. Plus everything that fell out of that 1 bracket expansion.
Right, polarization, the parallelogram law, the law of cosines with Pythagoras hiding inside it, and Thales' theorem. One algebraic move, paying dividends all afternoon. So the exam instinct, when you need a bound, square it, expand, and reach for Cauchy Schwarz. And that's the real lesson today. One careful inequality, squeezed hard enough, hands you almost the whole of geometry for free. That's Cauchy Schwarz, And the geometry it unlocks, one inequality, and suddenly a space of bare axioms has angles, triangles, and 2,000-year-old theorems. Thanks for watching. Next time, orthogonality and Gram-Schmidt. See you in the next one.